Good afternoon, everyone. Today we are going to have a discussion about the week 9, live session 9, and we'll have first a brief uh, recap of the week, and after that we'll go to question answer session. Followed by we'll be having discussion on the question answers, whatever doubts you have, we'll cover up in this session. So let's wait for us for a while to join others, and after that we'll move towards the question answer. First we'll go for the recap. So let's start the session. So today we are going to discuss about the physics of the fiber optic sensing, and for that we will move with the today's topic, which is um, phase based um, um, sensing. So there are two things, which is one is DAS, distributed acoustic sensing, and two, the FBG, which is fiber break gating. So you can see here that phase modulation, which is based on the DAS, and the second is the wavelength modulation, which is FBG, can also um, both are having the two different properties and different application, where the phase is very sensitive to the temperature and pressure, while the wavelength is totally um, depends on the source, how which source we are using, and how the temperature gradient is happening, because this is also very sensitive to the temperature and pressure. And the modulation in the refractive index can be possible because of the pressure change, strain change, and temperature. So it is very difficult to understand because of what the wavelength has been changed, but it can be you understand based on the different FBGs are connected in the single fiber. The temp, because if it is a because of temperature gradient, then it can be easily understand that overall the temperature gradient contrast will be have the same impact on the all the FBGs, while the pressure sensor will be having the localized pressure because of the traffic on the bridge. Suppose if it is attached to the this sensor is attached on the bridge, and that's how it works. So what are the challenges? The challenge of the distributed sensing is, first thing is underground oil gas pipeline where it is connected. So the acoustic emission from the high pressure gas leak more than 10 bar can have the problem with the this kind of um, distributed sensing challenges. Then second thing is like, once the remote ground layer, if somebody is walking on it, so the ground vibration from the broader inflation also can affect this. So the traditional sensor measures a single point. Critical infrastructure requires monitoring physical perturbations continuously over tens of kilometers. Okay, moving towards the next thing, which is the phase modulated sensor. um, that is a phase OTDR. So there is in the schematic you can see that first thing is the line width, narrow line width source, then circulator where the light is propagating through the fiber sensor, and once this it is happening, the sensing is happening at this particular place. From there the relay backscatter light comes to the circulator, and whatever is not scattered, the it propagates towards the receiver side. And this is happening because of the phase shift due to strain. Suppose we are assuming the strain is the key parameter which we are sensing. So this is the thing. Then acoustic pressure wave impart physical strain on the optical fiber through the strain optic coefficient. This physical distortion changes the phase of the light propagating through that specific segment. So you can understand this what is happening in this. Then moving towards the next thing, which is the coherent receiver. Why do we need the coherent receiver? Standard optical receiver are blind to phase. They only detect intensity. To measure an invisible phase shift, the returning signal must be mixed with the undisturbed reference waves. So suppose this is the reference arm and this is the signal arm, both should be mixed to understand what are the changes happening in the phase, and that can be used, that the coherent receiver can be modulated into the intensity, and which can be detected by the photodiode. So that's why we need the important that's why the importance of coherent receiver is there in the phase sensing application. Moving toward the next thing, the extracting signal from noise, distributed acoustic DAS. So you can see here that with the time domain, fast time domain, the unreadable, unreadable in real time. But if you do in the slow time frequency domain, then it is very highly possible that can be magnitude can be increased in a such a way that it can be visible. So you can see that acoustic signature isolated here with the frequency and magnitude um, plot. Moving towards the next thing, the limit of the phase sensing is on depends on the three things, which is source coherence. A round trip length of a fiber cannot exceed the laser's coherent length. Monitoring 10 plus kilometer requires ultra low spectral width in the kilohertz range. The next thing, environmental noise. Ambient temperature drops and background vibration cause phase to widely fluctuate over 2 to 2 pi I, destroying absolute phase measurement. And the last thing is laser phase noise. The inherent instability of the laser of the reference laser determines the fundamental minimum detectable limit of the entire optical system. If you have any problem with the noise, phase noise, then it is a very much problematic for the sensing application, which is phase sensing especially. So what are the paradigm shift here? So the thing is like wavelength modulation. The breakthrough is in a linear medium, physical perturbation, bending, twisting, temperature can corrupt the intensity and the phase of light, but they cannot change its fundamental frequency or wavelength. How it can be changed? It can be only changed by the receiver tech, which is color blind indium gallium arsenide is detecting the generates identical photocurrent of for any current. So detecting wavelength shift requires precision spectrometer. So this is the receiver tech, and it requires the precision spectrometer, and which cannot be fluctuated by this physical perturbation. So the core technology is Bragg grating fiber Bragg gratings, FBG. What is there in the is this application is once the uh, broadband light input is given, the reflected light, scattered light, Rayleigh scattered light is coming out from the FBG has the information about the refractive index contrast in the FBG, and that's how we are understanding that what are the changes are there, how much the lambda, the specific distance in the FBG is there, and how much the effective refractive index is there for this particular rating because of the temperature or physical strain fluctuation. So it can be the structure is created by inducing a periodic change in the refractive index of the fiber core, and that we have that we'll discuss in the next session. Then the function, which is act as a precision optical filter, it reflects only one specific color and transmit all other. You can see here that the physical of the physics of the grating, the dielectric mirror, how it works. The grating functions identically to a dielectric mirror, while a single layer reflects a tiny fraction of light. Periodic spacing ensures reflection from each alternating boundary accumulate exactly in phase. And how it works: pi I, 3 pi I, 5 pi I, massive coherent reflection, constructive interference. You can see here that pi I phase shift upon reflection, and pi by 2 phase accumulation during travel. And that's how this all merging together and making it a strong reflection of particular wavelength. And how it works actually, the Bragg condition is required for this. Center back wavelength, which is the lambda b, which also shifts during the wavelength based on the wavelength, based on the temperature and the physical parameters. So lambda b is directly proportional to the 2 pi to n effective lambda, where n effective also the optical density of the fiber core, and the lambda is physical period, the exact spatial distance between the high and low layer, low index layer. So the reflected color is directly mathematically logged to physical dimension of the grating. How we can sense the FBGs? To sense it, when the fiber is subjected to physical strain or heat, the grating period expands. This physical perturbation manifests as a direct measurable shift in the reflected wavelength, resting state. So period lambda, where you can see that how the lambda is shown here with the power intensity with respect to the intensity, and once the heat or strain is perturbing to the sensor, the change in the period is by del, and this change, because of this del, it also changes the measured lambda b, so it will shift somewhere else. So we will measure usually the del lambda, and based on that we can say that the lambda shift is happening, and this is because of the heat or strain. So it can also be quantified, either it is based on the strain or based on the temperature gradient. Moving towards the next thing, which is coupled mode theory or wave depletion. So the coupled mode theory or wave depletion says that it is for the reflectivity. So the reflected wave, we can see here that how the incident wave and reflected wave are having the different exponential based on the grating length with wave amplitude. So the reflectivity is directly is equal to 10 h square kl at lambda b. So as the forward propagating mode travels through the periodic structure, it continuously couples its energy into the backward propagating mode. The incident field steadily depletes directly, feeding the growth of the reflected field. Moving towards the next thing, which is engineering grating reflectivity. The challenge is that detecting the Bragg wavelength requires sufficient reflected power above the noise floor. Engineering optimize coupling coefficient or grating length to near 99% reflectivity. How we can achieve that? We can achieve with the having multiple grating pattern in particular fixed length. So the baseline parameter, which is delta n, the change will be in order of 10 to the power minus 4. Length will be in the sensor length will be 3 mm, and wavelength will be 1.55 micron, reflectivity approximately 30. So lever 1, the increasing index contrast delta n. So increasing by this can also achieve the reflectivity more, but the problem is we can't achieve more reflectivity, we can't change the more refractive index, because there will be a certain germanium oxide to kind of compound or material, which can change a few in a 10 to the power minus 4 refractive contrast. That is quite sufficient if you go for that. But if you, the second thing, if you have the same refractive index contrast, which is 10 to the power minus 4, but you are increasing the grating length L, so provides more spatial distance for constructive interference accumulation. So you can see here that this equation fulfills all the requirement if you don't think about the n. So this reflectivity is already proportional to the L, and that's how we can achieve more and more reflectivity from 30% to 99%. So what are the sensor architectures for the synthesis? So here we'll discuss about the target measurement, receiver technology, environmental resilience, and spatial topology versus the phase modulated for the phase modulated DAS or OTDR phase OTDR versus wavelength modulated FBG. So first thing, target measurement for phase modulated DAS or OTDR, you can see the dynamic relative frequency, which is acoustics, while is in hertz. While in wavelength modulated sensor, absolute magnitude, strain or temperature directly we can measure. Moving toward the next thing, which is a receiver technology. Coherent receiver measures optical interference and beat signals, while wavelength modulated signals requires a spectrometer measures precise peak color shift. Next thing, environmental resilience, high susceptible to temperature and vibration phase noise, while the fundamentally for the wavelength modulated FBG sensors, fundamentally immune, frequency cannot be corrupted in a linear medium. Moving towards the next thing is a spatial topology, fully distributed, every meter of a continuous fiber act as a sensor. But here we can have the but here in the FBG we can have the localized also, localized point. Concentrated point sensors requires discrete engineering grating at specific location. Going toward the next thing, which is the inverse problem. The remaining challenge, while an FBG provides a precise measurement over a wavelength shift, a simple, let me check whether okay, it's working. A simple shift in lambda b does not inherently reveal that caused it. Decoupling strain effect from thermal effect is the critical next frontier. So it can be also possible because of the strain or temperature, we can't distinguish, but it can be, it is a remaining challenge. But anyhow, if it is having the multiple sensors in the same fiber optics, then it can be understand that because of what, because of temperature or strain is happening. Okay, so let's take a 5-minute break, and after that we'll move to the question answer session. We have already discussed about we have recap of the previous for this week, and now we'll go to the question answer session. Let's wait for a while. Okay, so moving towards the question answer session, the first question here is, in a phase optical time domain reflectometer, phase OTDR, how are acoustic perturbations along an oil or gas pipeline primarily detected? Option A, by monitoring the polarization state changes resulting from pipe vibration, by picking up phase changes in relays backscattering light induced by pressure waves, by detecting the changes of the light wavelength as it passes through a crack, by measuring the reduction of a total optical power due to the fiber microbending. So most of you should understand that we are not we are not discussing about the wavelength, so it is not possible to discuss about this one. By picking up the phase change in Rayleigh backscatter light induced by pressure wave, and by measuring the reduction of the total power due to the fiber microbending, this is also not possible. We are discussing about the phase, so we have to stick with the phase. So by monitoring the polarization state changes resulting from the pipe vibration also possible, but in this two we need to discuss what are the things is important. So here the correct answer is by picking up phase changes in a Rayleigh backscatter light in Rayleigh backscatter light induced by pressure wave. This is the correct answer here. Moving towards the next thing, what is the primary reason of a coherent receiver is required for phase OTDR sensing rather than the standard direct detection receiver? Option A, standard receiver cannot handle the high power level of narrow line with lasers. B, standard receiver are only sensitive to intensity changes and cannot directly measure phase. C, coherent receivers are necessary to filter out the Raman and Brillouin scattering components. D, direct detection is limited to distances of less than 1 kilometer due to signal attenuation. What do you think about this? So the coherent receiver is required for the standard receiver are only sensitive to the intensity changes and cannot directly measure phase. So what is required here, that we need to introduce the um, uh, reference phase, reference beam along with the signal arm, signal beam, so it will be having the to measure the invisible phase shift, and returning signal must be mixed with the undisturbed reference waves, and that will achieve because of the uh, coherent receiver. That's why the correct answer is option B. Moving toward the next question, for a phase OTDR systems is a system to function over a distance of 10 km, what must be true regarding the light source? A. The spectral width del nu of the laser must be in order of kilohertz. B. The laser wavelength must be tuned to exactly point 0.8 micron for maximum Rayleigh scattering. C. The source must have a high pulse repetition rate to overcome fiber disruption. D. The source must be a broadband LED to ensure high spectral density. So, what is the conclusion here? So the correct answer here is the spectral width del nu of the laser must be in order of kilohertz. Then a narrow line width correspond to a long temporal coherent length which must exceed the round trip propagation distance for stable beating at a receiver. Okay. Moving towards the next question. In distributed acoustic sensing dash, what does the slow time axis represent in the context of signal processing? Option A, the propagation time of a signal pulse through the fiber length. B, the response of a fiber measured across successive pulses launched over a long time scale. C, the time is it takes for a pressure wave to travel from the leak to the fiber. D, the delay introduced by the electronic processing unit at the receiver. So the dash does the slow time axis represents in context of the signal processing is the response of the fiber measured across successive pulses launches over a time scale, longer time scale. Moving toward the next question, which is what is considered the fundamental limitation for the minimum detectable signal in a phase OTDR sensor? Option A, the laser's own phase noise. B, the thermal expansion of the oil pipeline being monitored. C, the maximum power limit of the indium gallium arsenide receiver. And D, the cladding diameter of optical fiber. So the fundamental limitation here is clearly it can be seen as the laser's own phase noise. If you have random coherency, random phase is coming from the laser, may perturb the actual phase noise, phase signal, and because of this noise, we will get the um, corrupted signals, corrupted informations. Next question, why are wavelength modulated sensors generally more robust against environmental noise in the lead in and the lead out fiber compared to intensity modulated sensors? Option A, spectrometers are more sensitive than standard photodiode to low light level. B, wavelength information cannot be altered by linear perturbation like fiber bending or twisting. C, wavelength modulation signals travel faster than intensity modulated signal. And the last option is D, the fiber used in wavelength modulation is made of a different glass material immune to noise. So you can see easily here the correct answer, which is wavelength information cannot be altered by the linear perturbation like fiber bending or twisting. Moving towards the next question, in a fiber Bragg grating, what determines the Bragg wavelength lambda b for wavelength for light incident normally on a grating? So it's just a simple question. Lambda b is equal to 2 and effective lambda. How does an FBG respond when subjected to physical strain? The Bragg wavelength shift toward longer wavelength. B. The reflectivity drops to 0 due to the loss of coherence. C. The reflected wavelength shifts towards the blue, shorter wavelength end of the spectrum. D. The index of the refraction increases, cause the light to slow down without changing the reflected color. Talking about the C, physical strain. So what is happening here? The physical strain is is directly proportional to the grating period. Strain increases the length, and we know that period, and we know that the lambda b is equal to 2 n effective del. So it means, like, if it is increasing, then del B also will increase. So that's why the correct answer will be the first one, option A. The Bragg wavelength shift towards a longer wavelength. Moving towards the next question, which parameter describes the percentage of optical power content within the core of the fiber, influencing the coupling of coefficient K of an FBG? Option A, the coupling ratio alpha. B, the coefficient factor eta. C, the strain optic coefficient P12. D, the spatial detuning constant. So this coupling constant so the parameter is the confinement factor eta. So the confinement factor represents the overlap between the optical field and the physical core where the refractive index perturbation exists. So if it is confinement factor describes the percentage of the optical power contained within the core of the fiber, influencing the coupling coefficient of an FBG. So this is the correct answer. Moving towards the next question, which is, I think, last question. Yeah. Using a formula R is equal to 10 h square KL, what happens to the reflectivity of an FBG if the length of the grating is increased while keeping the coupling constant K constant? The reflectivity remains the same, but the bandwidth of the peak narrows. B, the reflectivity decreases as the light has more distance to attenuate. C, the reflectivity increases. D, the reflectivity fluctuates sinusoidal according to the phase matching condition. as we know that reflectivity is directly proportional to L. So reflectivity of FBG, if the length is of the grating increases, so it will be increasing. It's directly R is equal to directly proportional to R is proportional to L, and that's we have finished all the questions and discussion. Now I will close the session here. We will move to the next class and also discuss about few things next week. Thank you so much for joining. So yeah, so let's close the live session today. We'll meet next week.